All right, today we're going to be looking at section 2.6, continuity. And in this section, they kind of basically talk about what a continuous graph is and what continuity means. So most of the graphs that we talk about with continuous, they use an example of like a fish growing, but you can think of a human. Usually their height starts at a certain point and they grow continuously with no breaks or jumps. Versus if you look at a parking meter and you insert quarters, you got 25 cents and you got another quarter, so it jumps up to 50. There's no connection between the 25 and 50, and you get this what they call a step function. So we're going to describe what continuous is. It says this is informal, but f is continuous at a if the graph of f does not have a hole or a break at a, and that is the graph. That is, if the graph near A can be drawn without lifting a pencil. So a really good way of thinking about what it means to be continuous is, can you draw it without lifting up your pencil? And then they talk about some special scenarios that we want to think about that will get a little bit more advanced as the definition becomes a little bit more precise. So the first definition, continuity at a point. A function f is continuous at A if the limit of f of x as x goes to a is equal to f of a. Now this has more than one part, as it says here, so that one definition really has three parts. So here's the checklist. So in order for f to be continuous at a, we have to have these three conditions hold. F of a is defined, so you get some value. Then the limit as x approaches a exists, and the limit as x approaches a is equal to f of a. So you get all of these different pieces working at once if it's continuous. Then we talk about discontinuity. So if it's not continuous, or points of discontinuity. And so you can kind of see here, so we've talked about what it means for a limit to exist. So if we look at the point 2, as the graph approaches 2 from left and right, we do say that the limit is equal to 1. However, the function f of 2 is defined to be 3. And so by this definition, it is defined, the limit does exist, but the limit is not equal to f of a. So this is a point of discontinuity, or the graph is discontinuous because it has a hole. So same thing with asymptotes. If you have an asymptote, there's a break. You got to draw your graph up, and you have to pick your pencil to go on the other side of the line. And so you can kind of look at all of these, and it kind of talks about the removable discontinuities, jumps, and infinite discontinuity. You see a few examples here. Then we go over continuity rules. Have theorem 2.9. It just tells you if you have two continuous functions, f and g, and they're continuous at point A, you can apply the same rule. F plus g will also be continuous. F minus g will be continuous. C, some constant times the function f, will be continuous. F times g is continuous. F divided by g is continuous, provided that g of a is not equal to 0. So whatever's on the bottom can't divide by 0. And then f of x to the nth power will also be continuous. So this is just saying if they're continuous, then all of the following are also continuous. You have polynomial rule. So all polynomial functions are continuous for all x. Rational functions will be continuous everywhere except what makes the denominator 0. You get some examples and visuals. Continuity of a composite function at a point. If g is continuous at a and f is continuous at g of a, then the composite function f of g is continuous at a. And they show you some examples of that. And then we talk about limits of composite functions. So g is a continuous function at a, f is continuous at g of a. Then you get the limit of f of g of x as x goes to a is equal to f, the limit of the function. So the function of the composite function is equal to the function of the limit. So you can still find the limit of g of x, plug it in to f, and you get the same thing. If the limit of g of x as x goes to a is equal to L, and f is continuous at L, then we know the f of g of x as x goes to a is going to be equal to the same thing. They're just showing you in limit form. If it's continuous, and then the limit will work as well. And they go through the proof of it, which is neat if you want to spend time reading and going over those. And then continuity on the interval. So we talked about endpoints. So a function f is continuous from the right, or right continuous at a, if the limit of f of x as x approaches a from the right is equal to f of a, and f is continuous from the left, or left continuous at b if the limit of f of x as x approaches b from the left is equal to f of b. So you can go from the right hand side and see that it approaches a number, or going from left to right, and they're just showing you that. So right continuous means you end at a point, left continuous means you end at a point. This graph on the top is not left continuous, so as you go from left to right, you end up at a discontinuity. Continuous on an interval. A function f is continuous on an interval I if it is continuous at all points of I. If I contains endpoints, continuity on I mean endpoints from the right or left at the endpoint. So it's also continuous in the middle and at all points. So you like a cold interval, connected interval. And then you have some examples and visuals. We have some involving roots. So continuous with roots, assume n is a positive integer. N is in, if n is odd, then you have f of x to the 1 over n power is continuous at all points at which f is continuous. If n is even, then f to the 1 over n power is continuous at all points at which f is continuous, and f of a is greater than 0. So it's got to be positive. When you deal with even powers have to have a positive under that square root. And you got some examples of that here. And then we talk about transcendental functions or trig functions, exponential, inverse. You get to see some of those same properties being applied. Continuity of an inverse function. If f is a function continuous on an interval I and has an inverse on I, then its inverse, f inverse, is also continuous on the interval consisting of the point f of x, where x is in the interval I. So that's just a definition. And then they show you some of those, and then some of the continuity of transcendental functions. Says the following functions are continuous at all points of their domain. And so you got to know their domain as well. Then you have the intermediate value theorem. So a common problem in mathematics is finding solutions to equations of the form f of x equals L. Before attempting to find values of x satisfying the equation, it is worthwhile to determine whether a solution exists. So the intermediate value theorem is probably a mouthful when you read this definition. However, it's really not difficult to understand when you look at the visual. So intermediate value theorem says suppose f is continuous on the interval AB. So a is an x value, b is an x value, and L is a number strictly between f of a and f of b. So we're now saying there's a y value that is between these two x values whenever you associate a point. Then there exists at least one number c in AB satisfying f of c is equal to L. So if you were to kind of draw a open interval or a interval between a and b, those points would map to y values, and we pick a y value between those two y values associated with a and b, and there is a point in the middle. If we go backwards and find the y value, we can trace it backwards and find the x value such that it equals to that y value. And so you got some visuals here. Sometimes if it's not continuous or if there's a break, that would break the that definition breaks down a little bit if it's not continuous, but again you got to go on that it's continuous function, so that means you wouldn't have a break. So if f is not continuous, then it won't work. So make sure you wholly understand the definition. All right, with that, we're going to jump over to MyMathLab and work a few examples.